Hello everyone. In this video, I want to try to show a visual understanding of the sine formula and the cosine formula in the complex realm. These formulas are kind of convoluted. They have a lot going on in them. You have e to the xi, you have e to the negative xi, and just add them and subtract them. So it's pretty ugly to look at first glance, but it's actually quite simple to arrive at them. And I would say it's equally as simple to understand them visually. So I'm assuming in this video that you're comfortable with Euler's formula, right? E to the xi equals cosine of x plus I times sine of y of x. I'll assume that you're pretty comfortable with this formula, that you already understand it quite well, or even if you don't, that you're just okay with it being there and that it makes sense to you. So with this out of the way, let's just recap what this formula really is saying. If we go down here, we have a little complex plane with a circle in it. Let me denote here real quick. This is the complex plane. So horizontally we have a real axis. This is where our real numbers are in. And vertically we have our imaginary axis. That's where our imaginary numbers are in. So we have our little circle here, and let's consider this to be the unit circle in the complex plane. Let's consider this to be a circle where the distance from the origin to the circumference equals 1. Right? Equals 1. And we know that when we have a circle with distance 1 from the origin, if we cross a radius at any given angle, let's say this angle right here, let's call it theta, the height of this triangle is going to be the sine of that angle, and the width is going to be the cosine of that angle. If you're wondering why, well, it's just simply because we have a triangle, right? A right triangle with hypotenuse 1, right angle, and if you consider this angle right here, right, we know that sine theta, there you go, sine theta equals the opposite side over the hypotenuse, and cosine theta equals the adjacent side over the hypotenuse. So since the hypotenuse is 1 in this case, then the opposite side is the sine of the angle, and the adjacent side is the cosine of the angle. So that's why the sides are sine and cosine. So with this out of the way, we know that this point over here, this point, which is a complex number, it has its real part being its width and its imaginary part being its height. So we can denote this number as its real part, which we know is cosine theta, plus I sine theta. So we know that any number in the complex unit circle can be denoted as cosine of theta plus I times sine of theta, and this is just, well, given by Euler's formula, this is just e to the theta I. So we can denote any number in the complex unit circle as e to the theta I, where theta is whatever angle that number finds itself in. So what I'm gonna do is do the following. So let us consider a certain number. Actually, let me draw it in blue. Let us consider a certain number, certain complex number, right, in the unit circle. It's at some angle theta from the x-axis, and so we can denote this point, this number, as e to the theta I. The same thing we did before. But now what I want you to do, what we will do is we'll denote another number, in specific the conjugate to this blue number, if you want to call it that, right here. Now the conjugate, it's simple. It's just, as a concept, it's just basically the same number except it's mirrored by the y-axis. So it has an angle theta of the horizontal axis, but instead of going up, it goes down. So we write down negative theta since it goes down the x-axis. So now we have e to the theta I here, and this, we're going to represent this point just by e to whatever angle this is, and that's negative theta times I. So now that you have these two numbers, now that you have both of them, I want to do something. Now that we consider both of them, what I want to do is I want to treat them as vectors. Treat them as vectors. Why? Well, because what we're going to do now is we're going to add both of them, simply to see what that gives us. So let's put our vectors here. You have the blue vector over here, and we're going to add the red vector into this one. So in vector addition, right, what you do is you grab the tail of the second vector and you add it to the tip of the first vector. So we're going to get this red vector, which is the same length as the blue one. Let me just do this. Now that we've rotated downwards, we add the tip here. It's going to be around here. And so you can see that our result will be in the x-axis. And that's kind of to be expected, right? Or rather in the real axis, since the conjugate is the same number as we had before, except it has negative height, but the same width. So the heights cancel out when you add them, and the width doubles. And you can see that it doubles because in vector addition, once you add two vectors, you get a resulting third vector. It goes to this point. And this third vector, which kind of overlaps the second one, but that's fine. This third vector, you can see that half of its size is given by the length of the blue vector and a bit of the red one, and the rest of the red vector. So basically half of this is the blue vector and the other half is the red vector. So we can see that its length, its width, is twice the original width. So this is twice the original width. But what's the original width? Well, we know that it's just going to be the width of this blue vector. But since it's a point in the unit circle, well, that's just going to be twice the cosine of whatever that original angle is. Right? And so, if we want to find the value of the cosine of the original angle, all we need to do here is simply just scale that vector down by a half. We're going to come here and we're going to scale this right here by a half. We're going to scale it down by a factor of 2. And so what we end up with is this relatively smaller vector that's half its length or width, whatever you want to call it. So this vector sits at a point that is the cosine of theta, with theta being your original angle. So let's recap the steps we took real quick. So first we considered a complex number, any complex number in the unit circle, which we can denote as e to the theta I, right? Next thing we did, we considered its conjugate, e to the negative theta I. And once we got these two numbers, we added them together. And then what we ended up with was twice the original number's width. And so, because we want the original width, since that's the cosine function of whatever angle we chose, we divided by a factor of 2. And after we did that, what we ended up with was simply just cosine of whatever the original angle was. So this is basically the meaning behind the formula. You're basically adding a coordinate that has a certain width and height to a number, another coordinate that has the same width but opposite height. And so when you add them, the heights cancel out, the width doubles, and then you divide that width by 2, so you get the original width, which happens to be the cosine of whatever angle you chose at the beginning. And it's really the same thing with the sine function. So in the sine function, things are a little bit more convoluted because instead of adding, you actually subtract things. So you consider your vector here, we have this vector, then we have the red vector, not that one, that one's still blue. You have the red vector over here, and well, again, we can denote this number as e to the theta I, and the other number as e to the negative theta I. So what we'll do now is we'll do the following. We'll subtract the vectors. You consider the original vector, much like in addition, it stays intact. So in vector subtraction, we take the original vector, the second vector, right? The second vector is going downwards. It's kind of like this. But instead, this is addition. We want to subtract. So to subtract, well, subtracting a number is just adding one number to another negative number. So we'll add e to the theta I to negative e to the negative theta I. And negative e to the negative theta I is just whatever number is 180 degrees apart from e to the negative theta I. Right? Because if you multiply by -1, that's just walking 180 degrees anti-clockwise. So we'll walk 180 degrees anti-clockwise here. If we rotate this 180 degrees, it would end up somewhere around here. Right? And you can see that much like before, we have now a resulting vector that has no width but has twice the height. And that makes sense because since you're subtracting, because e to the theta I has a height and a width, and e to the negative theta I has the same width but opposite height. So when you subtract them, you cancel out the width and you add in the height. So the width gets canceled and the height doubles. So this vector is twice the original height. And what's the original height? Well, it's just sine, isn't it? It's sine of whatever angle you chose. So this resulting green vector will sit on twice the sine value. So again, we scale that vector down by a factor of 1/2. So it'll be somewhere around here. Right? It'll be somewhere around there because we scaled it down by a factor of 1/2. Or we scaled it down by a factor of 2. And now we have this, which is sitting at the sine coordinate. Except it's on the imaginary axis. So this is actually I times sine of theta. And we want a real result. So to get a real result, since multiplying by I rotates you 90 degrees anti-clockwise, dividing by I will just rotate you 90 degrees clockwise. So we divide this by I. We divide this by I, making it walk down 90 degrees, giving us finally the resulting vector that sits on the real axis. End up with this vector sitting on the real axis, and this vector's value, it's just sine of the original angle, right? So again, let's recap what we did. We considered a number in the complex plane, in the complex unit circle, e to the theta I, and we consider its conjugate, e to the negative theta I, right? And so then we subtracted the two, which made this motion of adding the second vector to the first, then flipping it 180 degrees, resulting in this bigger green vector. Afterwards, we scaled it down by a factor of a half, or by a factor of 2, to get it to the size that we wanted, and then we divided it by I to get it to the real axis, so we can have a real result and not an imaginary result. And this, in the end, gave us, well, as you can see, and as we did it, this just gives us sine of theta. So, again, it's quite simple, but I decided to go step by step here. My drawing skills aren't the best, but I think it gave the right idea of what's happening in this. So, there you go. It's quite easy once you think about each of the theta I as a coordinate, and you start thinking of vectors. Afterwards, it all just kind of comes by naturally, if you're used to dealing with that, of course. So, though it's not that hard to get a hang out of. But then you might ask me, okay, that's cool and all, that's nice, it might be a nice little proof, but what are these formulas useful for? Like, I mean, come on, we made a formula for sine, but I never learned that in high school. Like, I didn't use that, so what use does this formula have? That's a good question, because if you try to use this formula, for example, to find, let's see, what if you want to find sine of pi using that formula? Well, it won't help you, right? Because you'll have e to the pi I minus e to the negative pi I divided by 2I. And to find this, to find both of those, you need to know what sine of pi is. So it doesn't really help you in any way if you're trying to find the values of sine in the original domain, right? However, this formula does extend the sine function into the complex realm. So if you're trying to find, for example, the sine of I, well, you'll get e to the I times I minus e to the negative I times I over 2I. And this is just e to the negative 1 minus e to the first, which is just e, divided by 2I. And we can take out this 1 over I in here because that's just negative I. So that's negative I times e to the negative 1 minus e over 2. And you can throw this part into a calculator and solve it. And after you solve it, you just multiply by negative I and you get sine of I. And it's pretty cool. It's a nice little thing you can do. And you can have a bit of fun of it, you know, try to find some cool results for sine, and as well as cosine, you know, can do the same for cosine of I. And you can notice that most of the time, sine of I is going to be negative, it's going to be imaginary, or cosine is going to be real, and you can find all sorts of patterns in it. And I think the most useful thing from this formula that kind of comes from this sine of I thing, sine of a complex number, is that it serves as a sort of bridge between trigonometry and hyperbolic geometry. See, we in hyperbolic geometry, which I won't get too into or that much at all, we have the hyperbolic functions, right? So like you have the hyperbolic cosine and the hyperbolic sine. And hyperbolic geometry does have its, it's pretty applicable in physics. It has a lot of areas where it's used. Special relativity is one of them, if I recall correctly. Space-time does require some hyperbolic geometry for it to be understood properly. So these formulas, they actually connect cosine and sine to the hyperbolic versions, because the defining trait of hyperbolic functions, right, is that if you have the hyperbolic cosine squared and you subtract the hyperbolic sine squared, you get 1. And one function that satisfies this, right, that is an expansion to the hyperbolic cosine and sine, well, for cosine it's e to the x plus e to the negative x over 2. And for sine, hyperbolic sine, it's e to the x minus e to the negative x over 2. And you can see that these look oddly familiar to the formulas that we have here, right? And you can arrive at these hyperbolic formulas by inputting different stuff into the cosine and sine functions. For example, in sine, let's start with cosine since it's simpler. If you have cosine of I times x, this is e to the ix times I plus e to the negative ix times I over 2. And e to the ix times I is just, well, e to the negative x. And negative I times I is just 1, so e to the negative x plus e to the x over 2. And you can just swap these out since it's the sum, right? And we'll get e to the x plus e to the negative x over 2, which is the hyperbolic cosine of x. So we came to this nice little equality here using these formulas as a bridge between them. You can do the same for sine, though sine is a little bit more, it takes a little bit more steps, So you have, for example, sine of ix. Well, this will be e to the ix times I minus e to the negative ix times I, right? And then we divide it all by 2i, and this again will just be e to the negative x minus e to the x over 2i. And here's where the first difference, or the two differences, show themselves, right? Here we have 1 over I, and we also have e to the negative x minus e to the x. We can't interchange these two, so what we need to do is multiply this by negative 1, since it'll interchange that. But we also, if we're going to do that, we also need to multiply the original one by negative 1. So then we'll end up with e to the x minus e to the negative x over 2i. And so still have the I there, so we're just going to multiply this by I. So it cancels, right? Just multiply by I. And what you get at the end of all of this is, well, e to the x minus e to the negative x over 2, which is the hyperbolic sine. But since we can visualize it all in one go, I'm going to rewrite it down here. We saw up there that if we have cosine of ix and negative I sine of ix. This is the hyperbolic cosine of x, and this is the hyperbolic sine of x. And again, once more, this is a nice relationship between trigonometry and hyperbolic geometry that can be very helpful if you're dealing with one or the other, depending on the context, right? Knowing that you can just call back to a familiar scenario if you're dealing with hyperbolic geometry, or if you can just, escape using complex numbers with trigonometry, if you're dealing with just cosine and sine, like an integral, So, yeah, this is quite a nice thing to have. One of the ways we can prove this connection is, once more, by these formulas that we were hopefully able to visualize in this video. So yeah, I hope this at least shed some light into these convoluted formulas for some. So thank you for watching and have a nice day.